So we're going to be looking at the formation of stars. Now, the beginning of a star's life cycle just starts off with dust and gas. So we're just going to have loads of dust and gas floating around. Now, these dust and gas particles are going to exert an attractive gravitational force on each other. So what's going to happen is this dust and gas is therefore going to attract into or inwards. And this here is known as a protostar. Protostars are formed due to gravitational pull between dust and gas particles. Now imagine I have like 100 people all spread out across a certain street or on a road. Now imagine if I now take those 100 people and bring them in and push them all into one room. The first thing you're going to probably think of is, well, it's going to get very hot. And that's the same thing that happens here. As this dust and gas all compresses in and attracts each other, the temperature will increase. A lot of this dust and gas is made of hydrogen nuclei. So we have hydrogen nuclei, which will obviously try and repel each other. But because the temperature is increasing, this also means that the kinetic energy of particles will increase as well. This is because, as we know, the kinetic energy is equal to 3 over 2 times kT. And this would therefore mean there is enough kinetic energy to overcome the propulsive forces. And what that basically means is two hydrogen nuclei can therefore fuse to form helium, for example. This is what happens in a main sequence star. Due to fusion of hydrogen, there will be a outward radiation pressure. And this is balanced by inwards force due to gravity. We have an inwards force due to gravity, and this is balanced by this outwards force due to the radiation pressure. And this means that the star remains stable. This here is the sequence that our star, the Sun, is currently in. And it will probably keep burning for like another 5 to 10 billion years. Now, the more interesting part of a star's life cycle is actually what happens after its main sequence phase. And this actually depends on the mass of the star. So let's first look at stars which have a similar mass to that of our Sun. These stars will have typically a mass of 0.510 m0, where this m0 represents the mass of the Sun. So stars that are roughly half the mass of the Sun, or something that is roughly within the limit of 10 times the mass of the Sun, will undergo the following pathway after its main sequence. The reason as to why the main sequence of these stars comes to an end is that the hydrogen in the star runs out, which means that fusion can no longer take place. So there is no more that outward force of radiation pressure, but there is still gravitational attraction. So due to gravitational attraction, the outer shell of the star will collapse. And as it collapses, the temperature will increase. It might look something like this. We have a little core inside our star, and the outer shell is collapsing. And because of temperature increases, we can actually see that hydrogen burning, this is literally just a name for the fusion of hydrogen, and this will occur on the outer shell. Because we have hydrogen burning or hydrogen fusion in this outer shell, this will therefore now exert a massive radiation pressure, and therefore the star will expand into a red giant. Now, in a typical red giant, inside the core, you can get helium fusing into carbon and oxygen and other slightly heavier elements. As this star expands, we know that the gravitational force between everything is going to decrease. So what's going to happen is this outer shell is going to start drifting away from the core. So this outer shell will drift away, and we call these fragments nebula, and the nebula can go on to form other stars. For stars like our sun, with the remaining core, what you're going to get is a white dwarf. And in a white dwarf, no fusion occurs, but photons from previous fusion, i.e. fusion from when it was in its main sequence phase, will still not yet have all been released. So there'll be some photons still left over. And now, in this white dwarf phase, these photons will get emitted. And that is why we call it a white dwarf, because it looks white. But once the white dwarf loses all of its photons, it's no longer emitting anything. So it's now going to be called a black dwarf. And a black dwarf is simply just the same as a white dwarf, which is the core at the end of our sun's life cycle. But now there are no photons being emitted. That is the final stage for stars that are similar to our sun. Now let's look at stars which have a mass that is way bigger than the mass of our sun. Now at the end of the main sequence of a massive star, after the star runs out of hydrogen, just like with a star of mass similar to our sun, it will shrink, there'll be hydrogen burning, and it will then expand, but this time it will expand into a red super giant. Unlike a red giant, inside this red supergiant, inside the outer shell, you can actually get much heavier elements. You can get helium, carbon, oxygen, and you can get elements as heavy all the way up to iron, and you'll find this iron in the core of a red supergiant. If you remember from our fusion curve, the most stable element is iron, so iron cannot fuse to form heavier elements, especially not under these conditions. Now, a star like this is just so unstable because it's so massive. And what it's actually going to do is it will explode. And it will explode in something called a supernova. And we encountered supernova last time, but this is a different kind of supernova. And as you know, these are very bright. Sometimes you may even be able to see these in the sky with your naked eye. And this explosion is due to the sudden changes in pressure, and this is in the outer shell. So the outer shell will explode away. But what happens with the core? Now for these really massive stars, the core can go on to do two different things. If the core has a mass less than 3 times the mass of the sun, we form something called a neutron star. And this is where protons and electrons fuse to form neutrons, as suggested by the name. But if this core is really massive, and talking about mass greater than 3m0, where again m0 is the mass of our sun. Now because this core is so massive yet small, basically meaning that it's such a dense core. The gravitational pull will not let even light to escape. And this is known as a black hole. And I'm sure you've heard about those before. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.